Alright, so last time we solved this heat equation. This is a heat equation with K equal to 0.2, and the boundary conditions at the endpoints are called Neumann boundary conditions. And then you have ux0, the initial condition is 2x minus x squared, and we did a lot of calculations, and after hard work we got this as the answer. Now you might wonder if this truly is the solution, because it looks very cryptic, right? So we want to know if this does act like the heat equation that we know of, right? So to know that, I'm using Google Colab. By the way, if you don't know what Colab is, just go to Google and Colab, enter, and then you'll find the Colab. And you need a Google ID to get access. And basically what it is you can do Python here without having to install it in your own computer, right? So let's see. I'm going to do PyLab in order to have commands ready for plotting and all that. And what I'm going to do is I forgot to say the interval. The x is from 0 to 2. So let me get the x coordinates ready. X, I'm going to make it linear space from 0 to 2, and I'm going to divide that into 100 points or 101 points, like this. And I'll have to make the function ready. So what's our function? I'm going to make this function uxt. So I'm going to define that. So define uxt as the following. First, the y value, the height, will be given as I'll start by making it as a 0 value for every x. Oops, I shouldn't have done. If you do shift enter, this just executes as a program. That's something that I don't want to do. So I do enter, and then I do y plus equals to 2 over 3, 2/3. That's the very first term, right? And then now I need to peek at the formula again, but let's see, for n, this is the summation. The for loop is like the summation formula that you write in the sum. It's negative 8 over n squared pi squared, all this. So let's type that in. For n in range, n starts from 1 and it goes up till infinity, but we can't add until infinity. That doesn't make sense. It's just too much, right? So we will just stop at something like 100. You can make it like 1,000 if you want to. Yeah, let's make it 1,000. Or if the graphics doesn't seem like what you want, then you can increase this. The bigger your n, you allow your n to be, the more terms will be evaluated, which will give you a better view into what's happening. Okay. All right. So let's see. So to y, what we're going to do is we're going to add these terms in the sigma, which is negative 8 divided by n squared times pi squared. Times is the power. Okay, so that's the coefficient times. And then you have e to the power of something that has a function in Python. It's called exp of negative 0.2 times n squared times pi squared over 4, and then times t, right? So I'll just put times t here. Times cosine of n times pi times x divided by 2. I believe that's what it is. Yeah, n pi x over 2. Okay, maybe I forgot the negative sign. There's a negative sign. Okay, so I think this is it. And then after all that, we will make it return y, the y values. So we have this function ready. Now let's try to plot x and then y, x comma y. So be u x at time t equals to 0. So the second one is time t equal to 0. Let's plot it. I think I have to show it. Okay. So apparently this doesn't work. Let me do import matplotlib. Yeah, that's plt. Do that, and then I'm going to use plt.plot of x comma u, x comma 0. Let's see what that is. plt.show. Just a minute. There's a matplotlib inline. I have to make sure that it's inline. Let me try that again. What's happening? Oh, now it works. Okay. Good. Now that doesn't make sense because when you have initial condition, let me look, 2x minus x squared, this is the one that we need. So I better be getting 0 at 0 and 0 at 2. Why is this not giving us? It's giving me negative. Okay, there's something wrong with this. I'll do time t equal to 0.1. Maybe that's gonna be helpful. Okay. Apparently this is not what it should be. Did I mess up something?
Is it supposed to be times cosine or plus?
It's times cosine. Is this formula right? Is this formula? Oh, I forgot this one. I forgot this part. That's why. All right. Okay, it's good to know that math doesn't lie. Okay. So I need negative 1 to the power of n plus 1. Okay, good. So I'm going to redefine this. Now let's... Oh, that's better. All right. So you see that this is the initial condition where at 0, it's 0, at 2, it's 0, and the heat distribution is like this. Now, what do you think is going to happen if you allow time to proceed just a little bit? Then this part at the end, because we have the Neumann boundary condition, which means that the endpoints are insulated, so that there's no place for the heat to escape. So the heat in here is going to go towards to the endpoints, so that things in here will go up, whereas the temperature down here will go down, right? So if I go back and put time as 0.1, just slightly after, you see that the peak went down a little bit, and the endpoints, it was 0 before, but now it's 0.3, right? So let's add some more time. What if it's just 1? Then it went down further, 0.72, and see, the difference between the peak and the endpoints doesn't seem that much, but because that's the way that the graph is drawn. The difference between, in terms of numerical values, it's only 0.1, so it's pretty much the same. So if you let me just look up. Let's see. Matplotlib y axis range. Okay, so I'm supposed to do. Oh no. Right. let's put the access range. Where's the, oh, PLTY lim. All right, good. So let's put this in there. So I want to execute PLT.y limit as minimum 0, maximum 1. Okay. So if I set that and then execute this again, no, it didn't work. No, it's not working. Oh, maybe this is what I need to do. I will put PLT.y limit as 0, 1. Okay. Okay, that's better. All right. Okay, so you go from here's 0, and if you want to compare that, if you want to compare the two, I can plot it over the other one. Ux comma 0.1 Ux comma Ux comma 2, no, 1, and then yeah, let's just plot these three together. So what happened is that initially the heat distribution was like this. Because the endpoints are insulated, the orange line is like 0.1 seconds later, and then 1 second later it's like that, so it's pretty much even, right? And then if you want to add like time infinity, well, we can't do time infinity, but let's say time 100 seconds passed. Then you get this red line, which is basically a flat line at 2/3, 0.666, right? So that shows you how the heat equation proceeds, right? Okay. So it's kind of amazing that you can write down the heat equation, solve it, and then you can graph it, and then the result just works. It just works. It gives you the solution of the heat as you would thought. Okay.